Last time we earned one equation. For a single curve x of t, the path that minimizes a cost has to obey the Euler equation. The partial of g with respect to x minus the time derivative of the partial of g with respect to x dot equals 0. One curve, one condition. But nothing real is one number. A market maker doesn't just track inventory. There's the price, a signal, a hedge. A spacecraft has position and velocity in three axes. The true state is a whole vector of functions evolving together. So the question for this video is simple. When the thing you're choosing is not one curve but many coupled together, what replaces the Euler equation? And then, what happens when the path is allowed to snap at a corner? And what happens when it's chained by a constraint? Answer those three and we arrive at last at the doorstep of optimal control. Start by adding states. Instead of one function, let the cost depend on n of them, x1 through xn, and on all their rates of change, and on time. The functional j now integrates a g that sees the entire vector at once. The trick to handle it is the same one from video 1, applied n times. Hold every function fixed except one, say x1, and wiggle only that one. The functional has to be flat against that wiggle, so x1 obeys its own Euler equation. Now release it, hold all but x2, repeat. Each function in turn gives back an Euler equation. So we don't get one equation anymore, we get n of them simultaneously. For each I, the partial of g with respect to xi minus the time derivative of the partial with respect to xi dot equals 0. Stack the functions into a column vector x, stack their derivatives into x dot, and the whole system collapses into a single clean vector matrix statement. The partial of g with respect to the vector x minus the time derivative of the partial with respect to x dot equals the 0 vector. One bold line that secretly means n coupled equations. Let's solve a coupled pair so it's concrete. Minimize the integral from 0 to pi over 4 of x1 squared plus x1 dot times x2 dot plus x2 dot squared. And here's a twist. x1 is pinned at both ends, but x2 is pinned only at the start. Its final value is free. Write the two Euler equations. They come out tangled together. One says 2x1 minus x2 double dot is 0. The other says minus x1 double dot minus 2x2 double dot is 0. Combine them and the coupling resolves into a clean oscillator for x1. x1 double dot plus 4x1 equals 0. So x1 is a blend of cosine 2t and sine 2t. The boundary conditions, including a natural one from the free end, fix every constant. The extremal is x1 star equals cosine 2t plus 2 sine 2t, and x2 star equals minus 1/2 cosine 2t minus sine 2t plus 2. For a quant, those coupled functions are the market making state vector. Inventory, mid price, and an alpha signal don't move independently. They are linked. Each one earns its own Euler equation, and the equations are tangled together exactly like this. The vector Euler equation is the law of motion for the whole desk at once. Now question we keep ducking. What if the ends of the path aren't nailed down? In the vector world, free endpoints give us two things working together. First, the Euler equation still holds in the interior. That never changes. Second, a boundary equation handles the loose ends. The partial of g with respect to x dot dotted with the wiggle in the final position plus the bracket g minus that same partial dotted with x dot times the wiggle in the final time must vanish. That one boundary equation is a master key. Depending on what's free, you read off a different condition, and Kirk organizes all of them into table 4.1. Both ends fixed, just the endpoints. Final position free. The partial of g with respect to x dot is 0 there. Final time free. That g minus x dot times partial bracket is 0. Both free and unrelated, both conditions at once. and both free but tied to a target line, a single transversality condition. 5 cases, 1 equation behind them all. Watch the table do real work on one integrand. Take j equals the integral of t times x dot plus x dot squared. Its Euler equation integrates twice to give x star equals minus 1/4 t squared plus c1t plus c2, a parabola with two free constants. Now change only the boundary conditions and let the same parabola adapt. Case A. Final time 1, pinned at 1 and at 2.75. Two pinned ends fix both constants. X star equals minus 1/4 t squared plus 2t plus 1. Case B. Start at 1, final time 2, but the final value is free. Now table 4.1's natural condition replaces the missing endpoint, and we get x star equals minus 1/4 t squared plus 1. Case C. Start at 1, end pinned at 5, but the final time is free. The free time condition kicks in and solves for the clock itself. X star equals minus 1/4 t squared plus 2t plus 1, with the final time equal to 4. Same physics, same Euler equation, only the boundary conditions change, and the table tells you exactly which one to use. Every path so far has been smooth, but real decisions snap. A relay flips from off to on. A trading rule jumps from passive to aggressive the instant the book tips. When the control switches like that, the slope of the path, x dot, jumps discontinuously. The curve develops a corner. So we widen the rules to allow piecewise smooth paths, continuous but with a kink at some time t1 we don't know in advance. The honest way to handle it is to cut the functional at the corner. Write j as j1, the integral up to t1, plus j2, the integral after. On each smooth piece, the ordinary Euler equation still holds. The new physics is entirely about what must be true at the joint, how the two pieces are allowed to meet. Demand that the total variation vanish and let the corner location itself be free. Two conditions fall out, the Weierstrass-Erdmann corner conditions. The first, the partial of g with respect to x dot must be continuous across the corner. Its value just before the kink equals its value just after. The second, the bracket g minus x dot times that partial must also be continuous across the corner, same value on both sides. Give those two objects names because they will haunt the rest of control theory. The partial of g with respect to x dot behaves like a momentum, and the bracket g minus x dot times the partial behaves like an energy, a Hamiltonian. The corner conditions say even when the control jumps, even when the path kinks, these two quantities glide through unbroken. For a trader, the corner is the regime switch, posting a quote one instant, pulling it the next. The trade rate is allowed to jump, but the corner conditions name what cannot jump, a momentum and a Hamiltonian. Hold on to that Hamiltonian. It is the exact object Pontryagin's principle will be built on in the next chapter. Two quick examples make corners real. First, minimize the integral from 0 to 2 of x dot squared times 1 minus x dot squared with the path from 0 up to 1. The integrand is 0 whenever the slope is 0 or 1. So the cheapest paths are zigzags, flat stretches and 45-degree climbs, splicing slopes of 0 and 1, each with 0 cost. A whole family of broken extremals, all tied at the value 0. The straight line connecting the endpoints, the smooth answer, actually costs more, 1/8. Here, kinking is optimal. Second, the shortest path that has to bounce off a wall. Minimize arc length subject to touching a line. The corner conditions force the reflection to be symmetric. The angle coming in equals the angle going out. The same law light obeys, angle of incidence equals angle of reflection, falls straight out of the calculus of variations.